Welcome to another deep dive. Today we're plunging into, well, one of the really fundamental challenges in artificial intelligence, true reasoning.
Yeah, we're not talking about just, spitting out facts or text that sounds smart.
Exactly. We mean the deep stuff, devising and executing complex, goal-oriented plans, the kind of problem-solving humans do.
Right, that intricate planning.
So our mission today, to explore a really fascinating new AI architecture. It's called the Hierarchical Reasoning Model, or HRM.
And this isn't just another small step. It's quite different. It's brain-inspired and really challenges how we think AI can, well, think.
We're going to unpack its design, look at its, frankly, amazing performance, and explore what it means for future AI. Think of it like we're walking you through a key research paper, but, making it digestible.
Making sense of the dense bits.
Exactly. So what's on the agenda? We'll start with why current models, LLMs, often stumble on complex reasoning.
Yeah, where they hit a wall.
Then we'll look to the human brain for inspiration. Always a good place to look, right? Before diving into the HRM architecture itself. After that, we'll check out its results on some really tough benchmarks.
And maybe peek inside its mind a little, see how it works.
Yes. See its thought process, and finally, tie it all back to those brain principles. Sound good?
Sounds great. So reasoning in AI, let's define that first. It's really about creating and, crucially, following these intricate plans to get to a goal.
It's more than pattern matching. It's structured, multi-step problem solving, like running an internal algorithm.
Precisely.
And the current way LLMs often do this is called chain of thought, KIT. How does that work? And maybe more importantly, where does it fall short?
Right. So KAT basically externalizes the model's thinking. Instead of just giving the answer, it generates intermediate steps, language tokens, sentences.
Like thinking out loud.
Exactly like thinking out loud. Breaking down the problem step by step in words.
Okay, so like showing your work in math class.
Kind of, yeah. But it's often called a crutch because while it looks like reasoning, it has some pretty serious limitations.
Like what?
Well, for one, it's brittle. Really brittle. A single mistake in that chain, one wrong step, one hallucinated fact, and the whole thing can just collapse.
Well, I've definitely seen that. You get this long explanation, and one tiny error early on makes the final answer completely wrong.
You've hit it exactly. And beyond brittleness, CoT needs tons of training data. Plus, generating all those extra words, all those tokens, it takes time. High latency, slow responses.
Right.
But maybe the deepest issue, fundamentally, is the underlying architecture. The transformer, which powers most LLMs, is actually quite shallow computationally.
Shallow? What does that mean in practice? How does that limit it?
It means they're amazing at, say, recognizing patterns quickly, making associations, but they really struggle with problems that need deep sequential logical steps, like true step-by-step deduction.
They hit a ceiling.
They do. Much faster than a human would on a genuinely complex logic puzzle. Take something like extreme Sudoku.
Okay, not the ones in the newspaper.
Definitely not. These are designed to be incredibly hard for humans. They often need lots of searching, backtracking,
trying things out, hitting dead ends, going back.
Exactly. And even huge transformer models, much bigger than this HRM we're talking about, they just fall flat. They can't perform that kind of deep, sustained reasoning.
Okay, so if thinking out loud, the CoAT method, is a helpful crutch, but ultimately limited, then the real breakthrough needs something deeper, something internal.
That's the idea behind latent reasoning. Yeah, it's kind of the holy grail.
Latent reasoning, meaning the thinking happens inside the model's hidden states.
Exactly. The core idea is that language is mainly for communication, right? Not the actual substrate of thought itself. Our brains compute internally without constantly verbalizing every step.
So CoAT is like spreading all your working out across your desk.
Yeah, messy desk analogy works.
Whereas latent reasoning is like doing it neatly inside your head.
Pretty much. All that complex thought happening internally efficiently.
But that sounds hard to achieve in AI. You mentioned limitations.
It is very hard. Just stacking more layers, the simple approach often leads to vanishing gradients, makes training unstable.
Right, the gradients disappear.
And recurrent networks, which seem like a natural fit for sequences, they often converge too early. They basically stop thinking deeply after just a few steps.
They get stuck.
They get stuck. Plus, they usually rely on backpropagation through time, BPTT, which needs a lot of memory and compute power. It's expensive and, frankly, not very biologically plausible.
Okay, so lots of challenges. But like you said, nature often has solutions. Where do we look when AI hits these walls?
To the brain. It's the best reasoning machine we know, and it gives us a fascinating blueprint.
How does the brain handle this need for deep computation?
Well, one key thing is hierarchical processing. Different brain regions handle different levels of abstraction. Higher level areas, like parts of the cortex, deal with abstract planning over longer timescales. Think planning your day or even longer goals.
The big picture stuff.
Exactly. While lower level areas handle the rapid, detailed, immediate computations, like reacting to a sound or processing visual details.
So different brain parts working at different speeds, different levels.
Precisely. Which leads to temporal separation. These levels operate on distinct timescales. Like slow brain waves versus fast ones. Theta and gamma waves are examples.
Okay.
This separation lets the slower, high-level plans stably guide the super-fast, detailed computations happening at lower levels. It's like a conductor leading an orchestra.
Ah, nice analogy. The conductor sets the overall piece, the musicians play the fast notes.
You got it. And then there's recurrence, feedback loops.
Right. The brain's full of feedback loops.
Essential for iterative refinement. And crucially, the brain's way of doing this seems to avoid those huge credit assignment costs of BPTT that plague AI models.
So less computational overhead for learning.
Much less. So these three principles, hierarchy, temporal separation, and efficient recurrence, those are the core ideas HRM builds on.
Okay, that's a great setup. So how does the Hierarchical Reasoning Model, HRM, actually take these brain ideas and build them into an AI?
It's explicitly designed around them, aiming for that deeper computation. It has 4 main parts, an input network, then 2 recurrent modules, a low-level one, let's call it FL for the fast, detailed stuff.
The orchestra musicians.
Yeah, and a high-level one, FH, for the slower, abstract planning, the conductor, and finally an output network.
Okay, high level, low level. How do they interact? What's the flow?
The model runs over multiple high-level cycles. Think of these as major phases of thought. Within each big cycle, the low-level module, FL, updates many, many times, doing all the fast, detailed work.
Right.
But the high-level module, FH, updates only once per cycle. It takes the final state of the low-level module from that cycle and uses it to set the stage for the next cycle.
So the high level guides the overall direction, cycle by cycle, based on what the low level achieved.
Exactly. High-level strategic planner, low-level fast worker.
But you mentioned earlier that standard recurrent nets get stuck. They converge too early.
Yeah.
How does HRM avoid that trap if its low-level part is also converging?
This is really clever. It's called hierarchical convergence. Yes, the low-level module FL does converge within each cycle. It finds a kind of local solution, an equilibrium.
Okay.
But then, the high-level module, FH updates, it provides a new context, a new goal or perspective. This essentially kickstarts the low-level module again. It disrupts the old equilibrium and pushes FL to start computing towards a new local equilibrium in the next cycle.
So the high-level module keeps giving the low-level one a fresh problem, preventing it from just settling down and stopping.
You've nailed it. It allows a whole sequence of these nested computations. Each cycle builds on the last, guided by the high level. This dramatically increases the effective computational depth. It keeps thinking, keeps working over many steps.
That sounds much more like sustained thought, a really neat mechanism. Okay, what about training, that BPTT memory problem?
Right. BPTT needs memory that grows with the sequence length. OT memory for T steps, impractical for very long sequences.
So what does HRM do?
It uses a one-step gradient approximation. Instead of backpropagating through all the steps, it essentially approximates the gradient using only the information from the last state each module in a cycle. It treats the previous states as constants for that update.
Okay, that sounds much simpler.
It drastically reduces the memory needed down to, constant memory. It makes training scalable and much more efficient. It's based on some cool theoretical work on deep equilibrium models.
So efficient learning without needing to remember every single past step in detail. Clever. And you mentioned deep supervision, too, inspired by brain oscillations.
Yeah, another brain-inspired trick. The model runs in segments, multiple forward passes. After each segment, it calculates a loss and updates the parameters.
Frequent feedback.
Exactly, especially for the high-level module. Crucially, when it starts the next segment, it uses the hidden state from the end of the previous one, but detaches it. This stops gradients flowing too far back, keeping things stable. It also acts like a regularizer.
So more stability, better learning signals. Makes sense. And you also mentioned something about System 1 and System 2 thinking. Fast and slow.
Adaptive computational time, or ACT. Yes. Inspired by how we humans don't spend the same amount of effort on every problem.
Right. Some things are instant, some need serious thought.
HRM incorporates this. It has a component, trained with Q-learning actually, that decides at the end of each segment whether to halt computation or continue for another segment.
So the model itself learns how much thinking time a particular problem needs.
Exactly. It dynamically allocates more compute to harder problems. And the cool thing is, it achieves similar accuracy to models forced to run for the maximum time, but uses way fewer computation steps on average. Big efficiency win.
That's really smart. What about inference time scaling?
Oh, yeah, that's another neat benefit. Once HRM is trained, you can often improve its performance on really hard problems simply by letting it run for more cycles at inference time. Just increase the computational limit. No retraining needed.
More thinking time helps, especially for tough stuff like that Sudoku.
Precisely.
Okay, so under the hood, what are these modules actually made of? You mentioned transformers.
Yes, it uses a sequence-to-sequence setup. Both the low-level and high-level modules are built using encoder-only transformer blocks. And they include modern bells and whistles like rotary positional encoding, GLUs, RMS norm, standard good stuff from modern LLMs.
So combining the power transformers with this new hierarchical, recurrent, brain-inspired structure.
That's the essence of it.
All right, that's a fascinating design. But the proof is in the pudding, right? How did it actually do on those tough reasoning benchmarks you mentioned?
Ah, the results. This is where it gets really interesting. They tested it on 3 benchmarks designed to push reasoning limits. First, the ARC-AGI challenge.
Like an IQ test for AI, right? Abstract visual reasoning from few examples.
Exactly, general fluid intelligence. And RC-AGI-2, which is even harder, needing more compositional logic, multiple steps.
Okay.
Then, Sudoku Extreme. We talked about this puzzles compiled specifically because they're hard for humans, lots of backtracking needed.
How hard are we talking? You gave a number.
Mean difficulty of 22 backtracks per puzzle. Compare that to standard datasets, maybe 0.45 backtracks on average. It's a different league of difficulty.
Okay, truly extreme. And the last one.
Maze hard. Finding the optimal path in a 30 by 30 maze. Sounds simple, but finding the best path in a complex maze requires long reasoning traces.
Right, lots of potential dead ends. Okay, the gauntlet is set. How did HRM do?
The results are pretty remarkable, especially considering it used only 1,000 training examples per task.
Just 1,000. That's tiny.
Tiny. And crucially, no pre-training and no chain of thought supervision. It learned to reason from scratch on very little data.
Okay, so what were the scores?
On ARC-AGI, HRM, with only 27 million parameters, quite small by today's standards, got 40.3% accuracy. That significantly beat much larger CART models, like O3 Mini High got 34.5%, Claude 3.7 was down at 21.2%.
Wow, a smaller model, way less data, no Koki handholding, and it beats them soundly. That's impressive.
It really is, but the gap gets even wider on Sudoku Extreme and Maze Hard.
Oh.
On those tasks, HRM achieved nearly perfect accuracy, near 100%. Meanwhile, state-of-the-art COAT methods failed completely, 0% accuracy, zero. Even standard transformers of a simile size, trained just to predict the answer directly, also zero. They tried a much larger vanilla transformer, 175 million parameters, trained on 1 million examples for the maze task. It barely got 20% accuracy.
Okay, that's not just better, that's transformative. It's solving problems other advanced methods can't even begin to solve.
Exactly. It suggests HRM is capable of a fundamentally different, deeper kind of computation. It's a potential leap towards, universal computation, general-purpose reasoning systems.
It really challenges the idea that you just need bigger models and more data, doesn't it?
It certainly offers a powerful alternative to just scaling up and using COTI.
Okay, so when a model does this well, especially on tasks requiring step-by-step logic, you have to wonder, how is it doing it? What's going on inside? Can we see the internal algorithm?
That's the interpretability question, right? And they did try to visualize it. By looking at HRM's predictions at intermediate time steps, you get some fascinating clues.
What do they see? For the maze task, for example.
For the maze, it looked like HRM initially explores multiple paths at once, kind of hedging its bets. Then it starts pruning the bad paths, eliminates the inefficient ones. Then it sketches out a rough solution and then iteratively refines it.
That sounds really strategic.
Yeah.
Almost human-like exploration and refinement. What about Sudoku?
Sudoku looked more like a depth-first search. You could see it exploring possibilities down one path, then hitting a contradiction and backtracking, trying another path, just like you or I would do on a hard Sudoku.
Fascinating. And ARC, those abstract puzzles.
For ARC, it seemed to make more incremental adjustments, iteratively changing the grid step by step, moving closer to the target solution, a bit like hill climbing and optimization.
So it's not just using one fixed strategy. It seems to pick an approach that fits the task.
It really appears that way. It shows a kind of flexibility in its reasoning approach that's, well, quite rare and encouraging for AI models.
That adaptability is key. And it brings us back to the brain. You mentioned how brain regions have different dimensionality related to their function. Higher order thinking, higher dimension.
Exactly, the dimensionality hierarchy. In neuroscience, we can measure the complexity or richness of neural activity using a metric called participation ratio, or PR. Higher PR means the activity explores a larger, higher dimensional space.
Okay.
And studies, for instance, in the mouse cortex, show a clear pattern. PR increases as you go from low-level sensory areas to higher-level associative areas involved in complex thought. The ratio between high and low PR in mice is roughly 2.25.
So a measurable signature of this hierarchy. How does HRM compare? Did it learn this?
This is maybe one of the most striking findings. When they analyzed HRM trained on Sudoku, they found the exact same pattern emerged. The low-level module's internal state activity. Relatively low-dimensional, a PR around 30. The high-level module, much higher dimensional, PR around 90. Wow.
The ratio between them, high to low PR, was about 2.98, remarkably close to the 2.25 observed in the mouse brain.
That's incredible. So it wasn't explicitly programmed to do this, it just emerged from training.
Exactly. It's an emergent property. They checked an untrained HRM, no difference in PR between the modules, both low. So the model learned to organize its internal representations hierarchically, mirroring the brain.
And why is that high dimensionality in the high-level module so important?
Well, many standard deep networks suffer from something called neural collapse, where representations become less dimensional, collapsing into simpler patterns during training. This can limit their flexibility.
Right, they get stuck in simple ways of thinking.
But HRM fosters high-dimensional representations in its higher module. This suggests it's maintaining a rich internal workspace for complex thought, much like our prefrontal cortex is thought to do. It might be a key reason why it succeeds on these complex long-horizon tasks. That's a fantastic insight, almost like it develops its own internal executive function space.
Okay, stepping back again. How does HRM fit into the bigger picture? Other AI reasoning attempts.
Yeah, it builds on earlier ideas, for sure. Things like neural Turing machines, DNCs, universal transformers. They also aimed for iterative algorithmic computation.
Right, models that could learn algorithms.
But HRM tackles some key limitations those models had, like the premature convergence issue and the reliance on BPTT. And it uniquely combines this with the adaptive computation, the brain hierarchy.
Yeah.
It pulls several threads together.
And how is it different from, say, brain-inspired models that use hand-coded algorithms?
Big difference there is that HRM learns its reasoning strategies from data. It doesn't need someone to explicitly design the algorithm for Sudoku or maze solving beforehand. It discovers it.
And compared to using reinforcement learning to improve chain of thought, RL for code often seems to mostly refine or unlock capabilities already latent in huge pre-trained models, rather than learning fundamentally new reasoning mechanisms from scratch. Plus, RL can be unstable and data-hungry. HRM uses this dense, supervised signal within its continuous hidden states, which seems more efficient and leads to this deeper form of reasoning we've seen.
Okay, and the big one, Turing completeness. Is HRM computationally universal?
Theoretically, yes. Like universal transformers, it has the components needed to simulate any Turing machine, given enough time and memory. You know, the idea of a system that can compute anything computable.
The ultimate flexible problem solver.
Exactly. By addressing practical issues like convergence and training efficiency, HRM gets us closer to practical Turing completeness. It can actually do the complex search and backtracking needed for things like Sudoku Extreme, which is a big step.
This has been absolutely fascinating. So, to wrap up, the hierarchical reasoning model really does seem like a significant advance.
Yeah, leveraging that brain-inspired hierarchy, the multi-timescale processing, it unlocks substantial computational depth, data efficiency, and stability.
And its performance on tasks that completely stump other advanced models, even huge LLMs using CoT, with such small parameters and data, It really throws down a challenge to the dominant approach, doesn't it?
It really does. It shows there's a very viable, powerful alternative path towards general-purpose AI reasoning, a path based on internal computation depth, not just externalizing thought.
It offers a potential foundation for truly universal computation.
It seems that way.
Okay, before we finish, here's that provocative thought for you, our listener, to chew on. Considering that this HRM model learns to think by mirroring the brain's structure, the hierarchy, the different timescales, and even spontaneously develops that similar dimensionality pattern in its internal states. What does this imply about AI learning itself? If AI can genuinely internalize complex thought processes, moving beyond just thinking out loud, how might that fundamentally change how we design future AI? And, perhaps even more profoundly, could it change how we understand our own minds?